Well, for number 1 on problem sheet 5, the first one is going to be true because 300 equals 15 times 20. Okay, so we've shown that 300 is a whole multiple of 20. The second one is false because if you apply the division theorem, then you find that 35 equals 2 times 17 plus 1. Okay. The third one is true because 0 is a multiple of 5. It's 0, times 5. Okay. The next one is false because 0 is excluded. This is explicitly excluded. You can't talk about divisibility by 0. And the last one is true because negative 21 equals negative 1 times 21. Now obviously here I'm giving overkill. I'm actually expressing these results in terms of the division theorem. In reality, because we're very familiar with divisibility, we can just recognize these facts. Okay, so this is definitely overkill. I'm doing this for pedagogic reasons, just to relate these issues with the division theorem. Okay, well, so much for number 1. So question 2 asks us whether this proof of this theorem is correct or not. So let's just go through and see. We begin by, and I'm going to look at this both in terms of the logical correctness of the argument and whether it succeeds from a communicative point of view. Okay, so let's see what we've got. We begin by stating an initial assumption. There's no standard method being used here, so we're not sort of saying by induction or contradiction. We're just going to do some reasoning, but we state where we're starting from. We're starting with the division theorem, and then in particular, a consequence of the division theorem for when we are looking at divisibility by 4, the remainder is going to be either 0, 1, 2 or 3. So this is just an immediate consequence, a direct consequence of the division theorem. So we've stated the assumption, we've correctly derived an instance of that assumption, and we've stated an instance of that assumption. Let me see what we've got here. Therefore, any odd number has one of those two forms because the other two are even. So now I've particularized this fact. Okay, so I've got a starting fact, and then I've got a particular consequence or a particular case. Starting fact, then we specialize it, in fact. Starting fact is a division theorem, then we specialize it to this case of divisibility by 4. Then we look at a particular case and say odd numbers of that form. And then when I square, assuming the algebra is correct, so yes, yes, the algebra is correct. And in both cases, the result is 1 more than a multiple of 8. Okay, so that's correct, that's correct. I've made the observation that they're both 1 more than a multiple of 8. And then I sign off by stating that this in fact proves the theorem. So I've got a beginning, a middle, and an end. So it succeeds communicatively. I've given reasons for each thing. Notice I didn't just square these things. I didn't simply square them. I said I was squaring them, so that the reader's not left wondering what I'm doing. Now the reader might be a little bit puzzled as to why I started in this way, and that's basically experienced mathematicians can fairly regularly and moderately quickly come up with this kind of thing. If you're a beginner, it can take you longer. Okay, and then when I've done that calculation, I make a specific conclusion, and this was a conclusion to the reasoning, not to the whole proof, because the conclusion of the whole proof is to observation that this proves the theorem. This is the drum roll. This is where the cymbals crash. This is where we take a bow. We've done it. We're out of there. Okay, so the answer is, yep, it's valid, and we've just checked that it's valid by going through all of these arguments. Okay, let's move on to number 3. Where this proof is in fact valid. Okay, let's just make sure that it works on all levels. We're arguing by contradiction. Okay, so this is the beginning, and this is the beginning step. Suppose the conclusion's false. Then there'll be a natural number n for which A is not true, so there'll be at least one. Now by the first condition, okay, at A1, we know that the m can't be equal to 1 because A does hold at 1, so m is bigger than 1. So m equals n plus 1 for some n. Since n is less than m, we know that an holds, because m is the least one for which it doesn't. Then by the second condition, an plus 1 holds, i.e. am. That's a contradiction, and that proves the result. The only thing to notice is that here the n has been used in a quantified form, so this is a variable that's been quantified, right? Okay. In this case, what we're saying is if this fails, then there'll be one of these n's for which it fails. And at this stage, the n is sort of a variable. But at this point, when we put the m in, m is a specific number. We don't know what its value is. In fact, we're going to show that no such m exists. But on the basis of a false assumption, there will be a place where it fails. And m is going to be a specific number. So the m here is specific within the proof. Okay. When I get down to here, the n is also specific within the proof because it's equal to m minus 1. So in these cases, once I'm down here, I've got a specific m and a specific n. Up here, it's just a general n. Okay. So everything here is specific. Now, in fact, there never was such an m, and hence there never was such an n, because the conclusion as a result is valid. But within the context of this argument, these guys are specific. Okay. Here, this is a variable, it's quantified. All right? In any case, this is true. This is true. Okay, in question 4 now, on problem set 5. The first one is going to be true. Because if A and B are two least upper bounds, then because A is a least upper bound, and since B is an upper bound, you'd have A less than or equal to B, and because B is a least upper bound, and A is an upper bound, you'd have B less than or equal to A, so in fact A equals B. By being least, each one must be less than the other one, because being a least upper bound implies being an upper bound. So you'd have inequalities in both directions, so A would be equal to B. So in fact there's only one of them, okay? If there's one at all. Okay, the second one is also true. Because if A is a lower bound, so is any number B less than A. Okay? Anything less would be a lower bound. The next one's going to be false. And to show it's false, let me just give you a counterexample. Okay? Let's just take any interval. 0, 1. Any interval will do. An interval contains all the real numbers, in this case strictly between, between 0 and 1 inclusive. Closed interval includes the endpoints. So it's an infinite set. But it's got a lower bound, namely 0, and it's got an upper bound, namely 1. So it's finite. I mean, so it's not finite. Okay, the question asked us to show. Oh, lordy. The question was to show that if it's got a lower bound and upper bound, then it's finite is false. And it's false because it has a lower bound, it has an upper bound, and it's infinite. It's got all of the real numbers between 0 and 1 inclusive. Okay, stay awake. The next one is false. Okay, 0 is equal to order 7 integers, considered a subset of the real. Okay, well, what's the set? The set of negative integers, it's dot dot dot, minus 4, minus 3, minus 2, minus 1. Okay. But its least upper bound is negative 1, which is the maximum element. So in this case, the least upper bound is actually the maximum element. It's not 0, it's negative 1. Okay? Well, that's number 4 taken care of. Okay, so in number 5, let's look at the first one. We have to decide whether it says that B is the greatest lower bound of the set A. So let's take it step by step. That first part says that B is a lower bound. And this says if C's a lower bound, then B is bigger than or equal to C. Okay? In other words, it does say that it's a greatest lower bound. This says it's a lower bound, and this says that if we take any other lower bound, C, then B is at least as big as C. So we can't find a lower bound bigger than B. So B is the greatest lower bound. Okay, that was that one. What about number 2? Well, the only difference between these two is that we've got a strict greater than here. Oh, wait a minute. Not only is this not the case, but in fact, this is just plain false. Because this is talking about all C's that are lower bounds. But among those C's is the original B, because it's a lower bound. So if this was the case, then this would imply B strictly bigger than B, which of course is false. Let me say a little bit more about this, because in both of these two cases, what's going on is we have implicit quantification. Quantification over C is implicit. This says for all C less than or equal to A, for all lower bounds C, B is at least as big as C. In the first case, because it was talking about for all lower bounds, it actually captured greatest lower bound for B. In this case, because it's talking about for all lower bounds, it includes the original lower bound B, and that would mean that it has to be bigger than itself. So not only does this not capture that it's a greatest lower bound, it actually is just plain false. Okay? There's implicit quantification going on over here. And here, implicit universal quantification is exactly what you need to capture the greatest lower bound. In this case, it makes something that's false. What about this one? Let's just take A to be 0, 1. Okay? In this case, the greatest lower bound is 0. It's also the minimal element. And that's what I'm doing here, because here we're talking about B being strictly less than A for all A in A. But in this case, or in the case of any set where there's a minimal element, that minimal element will be the greatest lower bound, which means greatest lower bounds can be in the set, so they won't be strictly less than everything in the set. So that one doesn't capture it. I mean, I took this one in particular just to have something specific, but any set with a minimal element will be a counterexample. Because if there's a minimal element, that minimal element will be the greatest lower bound, and it's not strictly less than everything in there. So we can't capture greatest lower bounds if we include strict less than. Same here. Okay. Same here. It's Yeah, I mean, there's a difference here, but this one is not going to work. So, same reason, just take A equals 0, 1. And the fact there's something else going on here is irrelevant, because this already makes the thing not work. What about this one? Well, this one says B is a lower bound. That's okay. This says, combine that with that, that says if I look at any B plus epsilon, so that says for any number bigger than B, there's an A which is less than it, which is another way of saying that number cannot be a lower bound. Okay. For any number bigger than B, it can't be a lower bound because it's already beyond something in the set. Let's draw a little picture here. Okay, I've got some set A and I've got a B. B is a lower bound, so it's everything that's to the left of it. And what I'm saying is pick any B plus epsilon slightly to the right. There's a B plus epsilon. Then there's something in the set to the left of it. So the set actually goes to the left of that point. In other words, you can't make B any bigger and still be a lower bound of the set. So B is in fact the greatest lower bound. The answer is yes. Okay, it's another way of really saying this. It is a lower bound, and this is just another way of saying pick anything that's bigger and then it won't be a lower bound. Alrighty? Well, we've got this one captures it, this one doesn't, and it's false. This one doesn't, this one doesn't. This one captures it. And we are done.